absolutely fantastic. Our speaker tonight is Mr. Nate Hatcher.
Well, thank you. I can get the PowerPoint up here.
Yeah, sorry about that.
Thank you, Carol. Can everybody hear me okay? Okay. How about that? We're live. Okay, great. Well, I appreciate the opportunity to come here and speak with you today. It's great to see some former colleagues I haven't seen in a long time, and be talking about the basics of mass transfer rate modeling as they apply to CO2 absorption. It's a topic gaining a lot of emphasis here late with carbon capture and greenhouse gases and the like. So my talk today, I'll give you a brief history of process simulation. I think it's always good to step back and remember our roots. We'll talk just a brief word about the ProTreat simulator, which is one of many implementations of mass transfer rate modeling. We'll talk about some of the characteristics that go into true mass transfer rate modeling as they pertain to columns. We'll go back and revisit the ideal stage and talk about some of the key elements that go into a mass transfer rate model. What really distinguishes a rate model from an ideal stage model. I've got a short video clip we'll show and a case study to kind of drive some points home. I guess when we're done, if there are any questions, I don't know, Carol, if that's normal, happy to entertain those. So.
We have a spare mic to go around the room too.
Perfect, okay. Very good. If somebody has a burning question that they feel they need to have answered during the presentation, feel free to raise your hand. Happy to go into that. Okay, I'm going to start off here with a brief survey. Wondering if, just by a quick show of hands, how many of you have at least one process simulation software package in-house? Would you raise your hand? Looks like the room is almost full. Okay, if you wouldn't mind, keep your hand up or put it up again if you have more than one simulation package. All right, I'd say we're probably still a little over half the room. And of those of you that still have your hands up, how many of you run those multiple simulation packages because you don't trust the results? You may keep your hands up. Okay, great. We have one final question here, and I know there are a few of you out here. Just are there any of you involved with process simulation from the development end? I think Ven, you can raise your hand, and several others. Okay, need to know how many darts are going to be coming my way. So, well, seriously though, I think some of you are of similar trust as I am to process simulation software, and I write the software. Starting off in the operations and design business, there's a natural distrust that goes into the mode of simulation. And I hope to cover and give you a brief flavor for why that is the case. And hopefully you'll come out of this at least having an appreciation as to how a mass transfer rate model is different from an ideal stage model and what some of those expectations can be. Okay, so just to put things in simple form, when we talk about process simulations, we're talking about physical and chemical representations by math, equations, of the processes that take place in our process equipment. Some are empirical and some are physically based. those equations that we're going to have to solve start off with fundamental chemistry, although some of us as chemies like to forget that aspect of our job. Material and energy balances, equilibrium relationships, and then finally mass and heat transport. Let's see. I put this slide together to kind of give set the flavor for, in terms of a timeline for the development of process simulation. This is just a rough order for what we're talking about. And up on the top of the timeline here, can everybody see that? Yeah. We have some of the major engineering developments that have happened pertaining to column models. And on the bottom, we have the technology that was required to make those developments happen. So here in the pre-Cambrian period, you've got log tables, rules of thumb. We graduated with slide rules that enabled shortcut methods, McCabe-Thiele, probably in the late Cretaceous period. The calculator, that made some progress now. And one of the things that came out of that was the concept, actually the concept of a flash is very old. This is not intended to be an absolute timeline, but to give you a flavor of the order of things. So after ideal stages came about, and about that time we had some shortcut methods, the Fensky, Underwood-Gilliland methods, etc. When the mainframe computers arrived, that enabled some of the computations for some of the early rate-based simulators. And my boss, Ralph Weiland, the founder of optimized gas treating, was instrumental in some of that. And finally, the advent of the PCs has really brought rate-based distillation home to many people. So surprisingly enough, though, in my industry, which is primarily gas treating, rules of thumb are still very prevalent. A lot of mystique, smoke and mirrors still pervades the industry, and we're trying to get the word out to change some of that. Okay, so really, process simulation is, in some regards, nothing more than automating the calculations that we once did by hand. And the primary advantage that you get with a process simulator is really speed of computation. It wasn't that we didn't know how to do mass transfer rate modeling in years past. We didn't have the firepower to solve the equations in this lifetime with all the people in this room. That's really what we're talking about here. And with that technology, we're able to now do more realistic models and put models together that waste a lot of time in front of the computer when you don't really need to. I'll do a brief history on the ProTreat simulator. This all started back in the mid to late 60s with some of the research work that Dr. Ralph Weiland did at the University of Newcastle in Australia and in New York at Clarkson University. Initially, the technology was out there for doing mainframe computing. And an early work supported by Dow Chemical led to the development of a piece of software called Gas Plant and later Gas Plant Plus. And those products were designed to run on the mainframe. And unfortunately, about that same time period, the personal computer came out and made the technology obsolete. Some of that research work that went in resulted in a number of offspring technologies. The the rate frac in Aspen later, and it took 11 more years before the Mark I actually came out. So we've been running ProTreat since 2003. I was involved in those days on the user end, first in design and then later in operations and optimization in vetting the software, and that's how I became a believer in ProTreat. Real briefly, what does ProTreat simulate? Pretty much any alkanolamine for gas treating plus up to 2 or 3 solvent blends. We're now able to model physical solvents. The dimethyl ethers of polyethylene glycol, which are offered through licensed processes such as Selexol, Coastal AGR, Genisorb has their own solvent. Glycol dehydration, mono, di, and triethylene glycol, sorry, I'm stuck on amine. Specialty solvents, which are blends of some of these root amines that the vendors use under their trade names. Hydrocarbon, BTEC solubility in the solvents, and additionally we've recently introduced capability to do caustic treating with mercaptans, HCN, some nasties from refinery services like heat stable salts, phenol, and ammonia and sour water stripping. And most recently we've, with the version 5.3 that came out, have a corrosion coupon unit operation block that attaches to streams and monitors the corrosion due to H2S and CO2 in your solution as you run your simulator. So that's all I really want to say about ProTreat. Again, the purpose here is to educate you on mass transfer rate-based simulation. And when we get to that, true rate-based distillation, we're calculating directly the transfer of species in either packed segments or real trays, depending on the actual hardware that is in the system. In ProTreat, there is no translation from ideal stages to real tower internals. We start with real tower internals. So with that, you get the hydraulics computed at the same time the mass transfers computed. They're coupled, and that's important. One affects the other. In ProTreat, we also take into account the chemical reactions and ionic speciation that are happening in the solvents as they pick up acid gases or react with heat stable salts or alkali contaminants. And the reactions enhance, in some cases, the mass transfer that can happen. So not only are we accounting for vapor-liquid equilibrium, that gives the driving force for the rate model, but flows, temperatures, pressures, compositions also impact the actual separation that will take place by leveraging mass transfer also. Hopefully this will be a little clearer as we get through. And I just realized that I think I've got the old version of this presentation loaded on the machine. I don't know if it would be possible to switch over. We're going to need to in about 10 slides. So we're going to start very simple with our old friend, the ideal stage. And the ideal stage is pretty simple. The main assumption here is that the vapor out and the liquid out from a given stage are in equilibrium. In order to solve this stage, we have to take into account the material balances, the energy balances, and the equilibrium relationships. But there's nothing about mass transfer that goes into this equilibrium stage. See, there's a lot of empty white in here. I'm going to go ahead and switch to a video here. Let's see.
The behavior of the vapor-liquid mixture on the tray covers a wide range of flow regimes from bubbly to spray conditions, depending on the systems and operating conditions. This is a typical operating diagram. The horizontal axis represents the liquid rate, and the vertical axis represents the vapor rate. Of the various regimes of flow, the spray regime is likely to exist at the low liquid rate and high vapor rate region. Distillation performed under vacuum conditions is usually operating in the spray regime. The bubbly regime exists at the high liquid rate region. Here, the vapor liquid contacting is taking place under bubbly or frothy conditions. This appearance is typical of high pressure distillation. The intermediate region is the mixed regime, where the two-phase phenomena cannot clearly be defined as either spray or bubbly.
We wanted to give you a flavor for just comparing that black box ideal stage with the range of what you can see in a real distillation column.
There's only one.
Yeah. There we go. Just F5, I think. There we go.
You can just.
I can go forward here. Okay, so we'll get back to our presentation here. All right, we just finished up the ideal stage. These are some still shots from the video just to show you what things look like on the low end. Did I lose it again here, Carol?
We just need to.
All right. And as we raise the gas rate, you can see things churning up inside more, inside the column. And at high rate, it looks kind of like maybe like the inside of a tornado. This picture is showing the onset of flooding in structured packing. And flooding in packing is not quite the same as in trays. In packing, it is more gradual, the entrainment that you can get. And you can see the jets coming up above the packed bed here. Here's the crimp angle. And as we entrain the liquid up and out the column, that's what we're trying to avoid. Okay, so at this point, we need to understand a little bit about, I'm going to use the example of gas absorption as a mass transfer rate process. Some of you all may remember this from class with some, maybe not the most fond of memories. In a nutshell, the absorbing gas, if we're talking about CO2 for example, has to diffuse along a concentration gradient in the gas right adjacent to the interface. And this interface layer is kind of thought of as a resistance film, just like in heat transfer where you have a boundary layer. And so at the interface, the gas dissolves into water or the solvent. I'm showing that as the physical solubility component. And if there's no reaction, then the dissolved gas diffuses out into the bulk liquid here. So this is the concentration gradient we're talking about. If there is a chemical reaction going on, the gas will disappear by reaction, and this steepens the concentration gradient right near the interface. And in effect, it enhances the mass transfer. And the part of the liquid layer that contains the concentration gradient is a resistance film too. So mass transfer rates and separation on a tray, a real tray, or a little chunk of packing are determined by mass transfer coefficients. In the gas side, we've got a kGa term. The coefficient is actually kg. A is the area at the interface. And on the liquid side, we have a liquid side film coefficient, Kl, and the same mass transfer wetted area we talk about. And that's where this transport happens. So in the gas side, the partial pressure of CO2 in the bulk fluid compared to what it is at the interface, I've got that denoted by star. That is the driving force for mass transfer in the gas to the interface. In the same way, on the liquid side, we have the liquid CO2 dissolved concentration, that's C star. We assume equilibrium happens at the interface, but only at the interface. And then the resistance coefficient times the area times the difference between the equilibrium CO2 at the interface minus the actual CO2 in the bulk phase, either with or without reaction. If we have reaction, that CO2 concentration is going to be lower in the bulk liquid phase. So you'll notice that the gas side mass transfer and the liquid side mass transfer are described by almost the same equation. There's only one difference. We have different concentration units we're using, and we have this little gamma term. I think we're losing, may have lost the mic here. Can you hear me okay? Okay. All right. We have a gremlin in the equipment, it appears. Sorry about that. So tray efficiencies in gas absorption, especially in amine type systems, alkanolamines, are so low because the equilibrium stage calculation, it bases its calculations on the chemical solubility. But it's the physical solubility right here that is the real driving force for absorption. So the equilibrium stage model, in effect, can be thought of using a driving force that is orders of magnitude too big. We'll get into that a bit more. I think it'll become clear. In a real rate model, you see there's a lot more inside the box. It's not empty and white now. all the processes that are involved in mass transfer and heat transfer are included in the model. The gases have to diffuse through the vapor through a flexible interface, dissolve into the liquid through a process of diffusion. In some cases, if it's an amine, there will be chemical reaction involved. There are heat effects with that, activity effects with that. Heat that's liberated may drive water to vaporize back across the interface or result in corresponding temperatures that are different between the liquid out and the vapor outlet. The rate of mass transfer of each chemical species is what determines the separation on a tray or a packing segment. And so what differentiates and makes mass transfer a little bit harder than heat transfer is we're dealing with multiple entities transferring across this interface, not just heat, like in a shell and tube exchanger. We have equations we have to solve for everything that is transferring phase, but that's just more computations that are required. It really isn't anything that is horribly rocket science. So there's a lot of chemistry going on in the liquid phase here, and I also wanted to point out that equilibrium stage models can get the chemistry right, but only insofar as it affects equilibrium. But if diffusion or reaction kinetics are affected, equilibrium stage models can't really cope with it. Okay, so we're going to dive a bit further into our gas absorption example and look the rate of mass transfer of something like CO2 into the liquid depends on the mass transfer coefficient that we talked about and driving force. Well, it becomes more of a ball of wire when you start looking into what affects the mass transfer coefficient. Not only is it equipment dependent, it depends on the particular type of tray or packing that you're dealing with. Sieve trays perform differently than bubble cap trays and valve trays. The active area, the amount that the trays are loaded impacts the mass transfer coefficient, not just the VLE. The driving force is the concentration difference here I've shown between the interface and the bulk. So for CO2, this is the free acid gas concentration at the interface and the free acid gas concentration before it's reacted in the bulk liquid. This would be like your can of soda pop or beer. If you want to put more CO2 into your solution, you can increase the pressure or lower the temperature. Those both impact the physical driving force for mass transfer. The mass transfer coefficient, I've got KL with a 0 subscript or a superscript here, is very analogous to say a shell or a tube side film coefficient. And there are correlations that you can use for different types of trays and packing to compute KL or KG for that matter. So the science is really not that horrible when you get down to it. What's horrible is trying to tie it all together and sort out the data that you're receiving, because the experiments that we do to measure these coefficients, oftentimes all we can measure are the product of KL and A, or KGA is the common term that the mass transfer vendors like to throw out there. We've touched a bit on the enhancement factor. In the other chart I showed you, it was called gamma. In this, I've changed the notation to E. And this has several meanings depending on whose model you may be running. what the enhancement factor represents, if we go back to our previous slide here, is the ratio of mass transfer rates that happen when you have reaction divided by when you don't have reaction. That's just the strict definition of it. Some people just fit efficiencies and back into this number from data. To do it right, though, is a lot more work. You have to solve differential equations that couple reaction kinetics with diffusion. And I'm not going to go into that in this presentation because this is a basics presentation. We got somebody clapping back there, okay. Okay, so just to summarize now, our mass transfer rate depends on the area available for mass or heat transfer, the phase resistances, and the driving force. So the phase resistances are impacted by gas and liquid. I put loads, I really should have said rates, because we're talking about mass transfer rates here. Hydraulics depend on column internals, they depend on layout, vendor specifics, and physical properties. That's something we can relate to more easily. Density and viscosity and diffusion coefficients are functions of the temperature, pressure that we choose to operate our system at. We have power over the physical properties. And as engineers in a rate model, what you are inputting is the macro cosm. You're not putting in a enhancement factor or a tray efficiency. You're putting in temperatures, pressures, flows, things you can read from a plant DCS screen or read off of an engineering drawing. There are no fudge factors involved if you do this right from the start. One final point here. In an equilibrium stage model, the fundamental assumption is that the vapor and liquid outlet are in equilibrium. In a rate model, the rate of mass transfer really depends on how far away from equilibrium you are. So the extent that the phases are not or are in disequilibrium, that's what dictates how much mass transfer we can have. So the results in terms of gas treating, you learn how much CO2 and H2S or mercaptan are actually removed on each real individual tray and each segment of real packing. Now packing, what we're doing there is you'll take, say, a 10-foot tall bed of packing, and what we do is we chop that up into discrete segments. And much like integrating the area under a curve, we're solving each chunk of area and integrating that down through the column. So in a true mass transfer rate model, you're never asked for the number of theoretical stages. You're not asked for the liquid holdup per theoretical stage. You're not asked for tray efficiencies or HETPs. These are all calculated figures that can be done after the fact. And as I mentioned, what you are asked for are the real details in your plant. So no shortcuts being taken. You're able to model the plant as it really is. And I've got a brief example here to show you just how that can be advantageous. Now, I don't want to discount phase equilibrium. It is just as important to get the VLE right in a rate model as it is in an ideal stage model, because that gives you your driving force for mass transfer. If your driving force is wrong, your mass transfer rates are wrong, your column predictions are wrong. If your input is wrong, that's something else. Garbage in, garbage out applies with rate models just as much, if not more, than an ideal stage model. One of the things you'll notice on a true rate model, there's more garbage you have to input. I hate to say it, but because it depends on the actual hardware in the system, you have to specify some basic details about that hardware to make the model right. So again, phase equilibrium, not the whole story. We want to get the VLE right, so the rate model will follow suit. Okay, I've got a case study for a gas stream, 20% CO2, fairly high pressure, 16 bar gauge. I'm going to have to apologize for the SI units. This was written for the European audience. If we need to do some quick translations, I will do those. 16 bars, which is several hundred pounds, 40 degrees C, maybe 100, 105 F. And before we can send our gas to a liquefaction plant, we have to squeeze almost all of the CO2 out of that gas. So a typical specification, and this is an absolute max you want to target for CO2 in gas going to a liquefaction plant, is less than 50 ppm CO2. We have a question? Okay. Our lean solvent is a mixture of MDEA and piperazine, a little warmer, 350 cubic meters per hour. That's contacted in a 30 tray, 2-pass, 24-inch tray spacing absorber. Some of the other details are on the drawing here. So if I were going to do the way I started out my engineering career, if this were a real plant or a solvent vendor's run I was trying to match, what I would do is vary the number of ideal stages at this solvent rate until I matched the vendor's result or what my plant analyzer was measuring. In this case, ProTreat's rate model was showing less than a ppm by volume of CO2 out. If I go and look at how many ideal stages it would take to get less than about 0.15 or so CO2, the closest representation is 5 stages isn't too bad. We can't round to fractional stages. So I took this for our example and said, let's look at 5 stages and how does the performance compare to the rate model. And I've got plotted as a function of the tray count, 1 would be the top of the column, 30 the bottom. First, the temperature profile. And the liquid and the vapor temperatures in the rate model are pretty close to each other. And there's a bit of a bulge down near the bottom of the column. That same column modeled with those 5 ideal stages are the blue triangles. You can see the ideal stage model gets pretty close to the liquid and vapor outlet, but the whole inside of the column is significantly off on the temperature profile. In terms of the CO2 concentration, as we go up the column, we're removing CO2. I've plotted the equilibrium values above the solvent that the rate model is computed. That's this dashed red line here versus the actual CO2 outlet here. And you can almost come into this drawing and step off 1, 2, 3, by the old McCabe-Thiele method, 4. There's my 5 stages. Okay. Now, we're going to take a look at perturbing the system just a little bit. And this is fairly typical of these reactive systems. I dropped the solvent rate by 10 cubic meters per hour, which is just several percent is all. And what happened, the rate model's predictions, you can see the temperature, the bulge which was down at the bottom of the column has now filled up the column. The same 5 ideal stages give about the same profile. Temperature profile's not in horrible disagreement between the ideal stage and the rate model. But if I look at the CO2 profile now, the rate model says 2/3, about 60% of the column is pinched. And it's pinched because of this high internal temperature that's resulted. And the actual outlet, just with several percent less solvent rate, we've gone from under 1 ppm CO2 to 109 ppm. Our 5-stage assumption still ends up at 0.6 ppm. So if this were a real plant, and we have seen this in a number of places, or a design going out, and you were targeting 50 ppm, your model would be telling you you're meeting treating spec if it were ideal stage based. Only the true rate model gets that right. Okay, so just to kind of recap here, in our rate model, the answers don't depend on how well you can play the guess the tray efficiency game, or if it's a liquid phase reaction, guess a residence time. They depend on what the tower internals really can do. And because we're not taking any shortcuts down to the fundamental science level, what you have in a true mass transfer rate model is a virtual plant. So instead of picking parameter values to match the data, if you find that your simulation doesn't match a operating plant, start looking for what's wrong in the plant. That's how I became a believer in the software after it bailed me out so many times. I've watched over 35 or 40 amine units, and ProTreat was the only one that consistently hit the plant performance data. So why rate model? Again, I'm probably preaching to the choir now at this point, but the predictive power, if you want to know what a different type of tray will do in the same column, maybe you need to reuse your support rings. You can switch it out in less than a minute, probably tell what the difference is. In the case of selective gas treating, I would argue that a rate model is the only way to do this reliably. And because it's not taking any shortcuts even at the chemistry level, it works right with mixed amines. This is just an example of some real plant data that was simulated. This can really happen. This is a rarity though, I will say. This was a specialty amine solvent. He's nodding his head there. This can really happen. These high temperatures you can't see unless you have internal thermocouples in your column. This was a rare case that did. Usually you just see the gas and liquid ins and outs, and you wonder what's going on inside the column. Above 180 degrees, this column would be starting to chew itself apart with corrosion. Okay, so just to summarize, I think we're running short on time here. The advantages of a real mass transfer rate model are many, but the main two are it's completely predictive. In the same sense, you can predict heat exchanger performance once you know what the equipment details are and the phase flow rates. The separation is directed directly related to the column internals, not just the type of the internals, but to the mechanical features, weir height, number of passes, tray types, packing types, size, brand, material. Relates to the real hardware with absolutely no translation from theoretical stages to packing volume. Again, our separation depends on the fundamental physical and transport properties, and so does the rate model. So really, no need prior operating experience to get answers. That's how I started my career out. I'd go ask the Ron Rather in the room there what he thought I'd need for ideal stages in this tail gas treating column. So again, I will say though, even with the rate model, the best we can tell you is what a plant should be doing. And if it's not doing that, then it's your job as an engineer to go figure it out. But if you think there may be some trays in the bottom of the column, take the real trays out. You might find that you match the treating performance. Instead of varying ideal stages, you drop half the trays out of the column. And lo and behold, the performance matches. That might be a good incentive to go spend a little more money and do a gamma scan on a column. But you have a little backup before you go and order that $10,000 or $15,000 testing. So just in the end, I'd like to close off by saying we're trying to take the guesswork out of process simulation. Thank you for your time, and take any questions.
Thank you very, very much. All right, I know that it's after 9 o'clock and we all would like to get home. So do I have two really good questions? No? Nobody has questions? One good question? One question?
Oh, now they're coming up.
Oh, all right.
Got three now.
All right, we'll do these three, because you guys raised your hands.
The reactions that you were talking about, they're occurring in the gas film. Is that correct? Or
These are liquid phase reactions, actually.
liquid phase reactions?
Yes, sir. Mm-hmm. Yeah. Yeah. But they happen right near the film boundary. Yeah. In the case of CO2, the hydrolysis with water is slow, and that's what controls the mass transfer rate. Wasn't trying to make gas treating specialists out of you tonight, but there's some more subtle details there. Go ahead.
Can you apply this to chemicals as well as, I mean, theoretically, obviously you can, but is it done, or how do you, where do you get the data, for instance, for formaldehyde, water formaldehyde, or methanol system, for instance, which has got the same problem with kinetics that are really important to it?
There are a number of mass transfer rate models out there, and I'm not going to advocate a particular brand or another, but several of those folks are in this room. I'll just tell you, I believe Aspen can do those sorts of things. My boss's former colleague, Ross Taylor, developed a rate-based model at Clarkson University. I believe it's called ChemSep is the name. You can Google that. Yeah. Dr. Taylor might be able to help you out. We cannot right now, someday.
You talked about CO2 absorption, and people are talking about CO2 capture and all this. I don't know if you ever think about what do you do with all the CO2 that's captured?
I don't know that I'm going to want to answer that question. There are various schools of thought there, some more crackpot than others. The latest is you inject it down to the ocean floor where the pressure is high enough, and you form hydrates and store it in the form of hydrates. And all that's great and hunky-dory until there's an earthquake or a volcanic eruption occurs, and all that CO2 is displaced. So that would be a good one to chat about at the bar afterwards.
I have a question still that CO2 or sulfur removal. When you use your simulation, do they like Rexel or Selexel? Do you have the plant data you can compare use your simulation, how they match each other?
All of the systems I showed you, we've, I can go back, let me find the slide here. Hopefully I won't lose the presentation again. Yeah. Where is that? Getting close here. Okay. One of the things we like to pride ourselves in at Optimized Gas Treating is that our models are backed up by plant data. So all of these systems you see here, we've validated before we came out with them versus plant data. And several of the people in this room have been instrumental in furnishing some of that data. This gentleman up front, I won't say his name, but sulfolane, in theory, we can handle. We haven't had the blessing or incentive enough to get Shell Global Solutions excited about sulfonol so we can put it into ProTreat. It's just a business decision at this point. So.
No more people jumping onto questions. Mr. Hatcher, would you please stay behind for a few minutes to
Sure.
answer any other questions that anybody has?
You bet. Yeah.
Fantastic. Thank you all. Or thank you so much.
No, you can turn it off. And here's a little gift saying thank you.
Thank you, Carol. Yeah, appreciate it. Should I give this back to Greg?